So as we have seen different type of flow regimes under multiphase flow, now we will proceed to multiphase flow models in FLUENT. Now do keep in mind that in this particular lecture, which is an introduction to multiphase flow modeling in FLUENT, we are not going to go into depth into all these models. What we will see is how to activate multiphase flow in FLUENT, and within each panel of multiphase flow settings, how to input different parameters and what type of such inputs and panels are available in FLUENT to model multiphase flow. So this is just like a primer or just like an initial overview of multiphase flow modeling in FLUENT. So under multiphase flow modeling in commercial software FLUENT, we have 4 different multiphase models: discrete phase flow model DPM, the mixture model, the Eulerian multiphase flow model, and the volume of fluid model. Among these, the discrete phase model, that is the DPM model, is a Eulerian Lagrangian type of model. The mixture model and Eulerian model are the Eulerian type of model. And the volume of fluid model is of course uses the volume of fluid approach. What we have seen is the different type of multiphase flow modeling options available in the commercial software FLUENT. When we sit to simulate our particular problem, the first question that comes to our mind is, which model do I use for this particular project or this particular multiphase flow problem? Now, to resolve this question, there are various guidelines that are presented within multiphase flow study literature as well as within commercial software FLUENT users guide as well as theory guide, and these guidelines are generally followed for selecting a multiphase flow model. So a type of matrix is available for us in order to select different multiphase flow models depending upon what type of flow regime exists in our problem, and then corresponding to that flow regime, which type of models are applicable. So let us start with the first flow regime, that is bubbly droplet and particle laden flows, in which the volume fraction is less than or equal to 10%. For such type of flow regime, we usually prefer the DPM model, that is because the Eulerian Lagrangian approach is applicable. Next is the bubbly droplet and particle laden flow, that is the same flow regime, but in this the dispersed phase volume fraction is more than 10%. In such cases, we cannot use the Eulerian Lagrangian approach, and hence we have to use the Eulerian approach. For such flows, the Eulerian model or the mixture model is applicable. The next flow type is slug flow, for which the VOF model is applicable because we have a distinct or separated phases with an interface between them. Another type is a stratified free surface flow. Again, as we have a free surface and a distinct interface between two phases, we use the volume of fluid model. Next type is pneumatic transport, in which homogeneous flow exists. For this, we use the mixture model, whereas for pneumatic transport granular flows, we use the Eulerian model. In case we are modeling fluidized beds, we generally use the Eulerian model. For slug flows and hydrotransport, we can use the Eulerian model or the mixture model. For slurry flows and hydrotransport, we can use the Eulerian model or the mixture model. In case we need to model sedimentation, it is generally preferred that we use the Eulerian model. Apart from these flow regimes, there are various other guidelines based on some terminologies or some basic physics. These terminologies are defined around the term called particulate loading. Particulate loading is defined as the mass density ratio of dispersed phase to that of the carrier phase. It gives us an indication of how the coupling is there between the dispersed phase and the carrier phase. That is, whether the dispersed phase also affects the flow of the carrier phase or the continuous phase. Is this coupling one way or two way, and also whether there is interaction between two droplets or two particles or two bubbles of the dispersed phase itself. So based on this, there are 3 types of categories: very low loading, intermediate loading, or high loading. When we have very low loading of the dispersed phase, generally the particulate loading number is very low. In such cases, the coupling between the phases is one way, that is, only the continuous phase is affecting the dispersed phase. Dispersed phase is not affecting the flow of the continuous phase. In such cases, we can use the discrete phase model, the mixture model, or the Eulerian model. Let's say if we have intermediate loading, in which the particulate loading number or ratio is average. In such cases, the coupling is two-way, that is, the continuous phase is affecting the dispersed phase, as well as due to the motion of the dispersed phase, the flow of the continuous phase is also disturbed. Hence, it is two-way coupling. In such cases, we use the discrete phase model, the mixture model, and the Eulerian model. So now for high particulate loading, in addition to two-way coupling, there is also particle pressure and viscous stresses due to particles. Hence, it is termed as four-way coupling. In such cases, we use only the Eulerian model.